So, hello, welcome back. So, as I said in the previous class that we will take up the Zeldo Frank-Kamenetskii analysis in this class. It is basically a derivation. I do not want to show it on slides, I want to do the derivation for you, and so please pay attention. This derivation, there are two purposes. The first purpose is that we will once again consider this planar laminar premix flame that is stabilized at x equal to 0 in a doubly infinite domain, that is x goes in the left hand side, x goes up to minus infinity, on the right hand side x goes up to plus infinity, and of course it is a laminar flame and there are no it is in a the flow is uniform and there is no non-uniformity in the flow. So, there is no stretch on the flame also. Okay. So, this is the Zeldo which analysis that we will do. Okay. So, so once again this is our structure of the flame. X equal to 0, that is the end of your reaction zone, or so we will draw the reaction zone later. So, your temperature varies like this. It is not linear because of the presence of both conduction, convection and diffusion. This is TB0, which is the adiabatic flame temperature. Of course, there is no heat loss, and we will call this as Xig, that is this temperature, and this temperature to be essentially a Tig. Okay. And from this Xig to this part is essentially minus, we will call this minus, we will call x greater than 0 to be plus. So, x less than Xig will refer it with this superscript minus, anything greater than x0 we will refer it with plus, and this inner part we will refer it as inner layer in. Okay. Similarly, there will be a species profile. Okay. This is YU, this is TU. Okay. And if you normalize, YU tilde is equal to 1 and this is TU tilde. So, everything can be normalized like this, Xig also can be normalized. So, this if you remember, the equations we started with were this way, F0 convective term minus diffusion term W is essentially the species consumption rate, and the diffusion and the species equation, convection term minus diffusion term this is not omega, this is W. All right. Now, when we normalize it by saying T tilde is equal to CPT by QCYU, we normalize by Y tilde is equal to Y by YU, and x tilde is equal to x by LD0, which is LD0 is the diffusion zone thickness, lambda by Cp by F0. This implies x tilde is equal to your x divided by lambda by Cp 0. Okay. Now then, if you normalize these things, the equations that you will get are much cleaner. So the normalization is what the pain, and it becomes much cleaner in the sense that you clearly see this is a diffusion term, this is a convection term, and that is given by minus dSE0 y tilde and then you normalize the diffusion equation, species diffusion equation, and you add it to the normalized temperature equation, and you will get okay. So once again, remember, we are just considering the diffusion species equation for the deficient species, because we then the other, that is the abundant species, can be assumed to be constant, and that is why in the reaction rate only the deficient species come in. All right. So now with this we can proceed, and first what we will do is that we will integrate this equation in 3 different zones. Okay, we will integrate the equation in this minus zone, we will integrate the equation in the plus zone, and we will integrate these equations in the inner zone. And then we will see there is one problem that we have to face, is that this temperature equation, while integration, it cannot be integrated directly, because when you integrate in the inner zone where this reaction rate is dominant, then you have to tackle basically this y tilde. Okay. So how do you tackle y tilde? So something has to emerge from this other equation, that is a coupling function equation, so that you can write this temperature equation in a purely temperature form. So we have to get rid of the y tilde in some other way. But before that, if we integrate across the minus and this plus, you see the most important thing is that we can conveniently set these right hand side in this temperature equation to be 0. Okay, so that is the advantage, because that in these regions, in the entire minus, so from x equal to infinity to my x egg, okay, there is no reaction taking place. So as I said before, that is a consequence of the fact that your activation energy is very large, and as a result of the activation energy is large, your reaction is only activated at very high temperature, right. So there is no reaction taking place at in this minus zone, there is no reaction taking place at plus zone. So in these regions, if we integrate, that is, if we integrate between minus infinity x to x egg tilde, then your right hand side w is equal to 0. Similarly, if you integrate between similarly if you integrate between 0 to x tilde to x plus infinity, then also your w is equal to 0. All right. So if you do that, what you get? What you get is the following. That is if we just integrate up to this boundary. So we are integrating from x equal to minus infinity . Okay. So this is of course equal to 0, because at x equal to minus infinity there is no temperature gradient. So then this equation becomes is equal to T tilde minus Tu tilde. Now you see that T tilde is very close to your TB0. So, in many cases we can do the approximation, of course depending on the case we can do the approximation that this is equal to, because this difference T minus Tu is so large, we can easily replace the error generated by replacing T with Tb0 is equal to very small. So, we can generate with this, and this Tb0 minus Tu tilde, as we have seen previously when we do the analysis, that is equal to 1. Okay. So, just refer to the previous class that when we did this integration, this Tb0 minus Tu tilde is equal to 1, and that came from this equation. Okay. So, when we just integrate this equation from minus infinity to plus infinity, what we got was that this went out, this went out, and we got minus Tu tilde plus yu tilde, which is equal to 1, is equal to, on the right hand side once again this went out, this went out. So, we got 0 plus 0 minus Tb tilde. Okay. So, as a result of that we got Tb tilde minus Tu tilde is equal to 1. Okay. So, that is the reason. So, now once we have got that, let us just store this data, let us store this in our memory, and we will come back to this soon after. Similarly, on the right hand side, if you do this, we will just on the right hand side, if you do this integration, on the right hand side you will find integrating dt tilde dx tilde, that there is nothing much to do on the right hand side, that is equal to 0. So, that is the only condition that you have, and that your t everywhere your Tu tilde plus is equal to your Tb tilde 0. Okay. So, that is all that you can have on the right hand side, that is on the plus side. So, we will just remember this, and we will just store this, actually let us write it, keep it stored in the previous class, in the previous slide. So, your dt tilde plus dx tilde is equal to 0, and your t tilde plus is equal to your Tb0 tilde. Okay. So, these are the things that you have. All right. So, now let us focus on the inner zone, and this is the most important thing, because here you see this is challenging, because in the inner zone you have your temperature equation d2t tilde, you have the temperature equation like this, d2t tilde dxs square tilde minus d tilde dx tilde is equal to minus dAc0 y tilde e to the power of minus Ta tilde by T tilde. So, the basic problem is that, yes, of course, this is challenging because there is a nonlinear term e to the power of minus Pa by T, but this is even more challenging because this is you see here this thing has come in, right. So, you have a yu tilde, that is a different variable. So, you have to solve it in a coupled manner, which is very difficult. So, we have to get rid of that sometime. So, for that, to get rid of this, okay, what we will do is that we will consider this other equation, that is a coupled equation, that is d2t tilde. So, if you are not if you feel uncomfortable about these equations, I suggest you just go back and derive this equation yourself from the one dimensional energy, from the simple diffusion control system equations. You derive your one dimensional equation, you go through the derivation once again, and then you normalize it yourself, and then you come back and do this derivation again. You can just pause this video, right. So, so I suggest you, before you, if you are not comfortable with this equation, you should just take a pause and go back to this derivation, and then come back and then go through the analysis, because this to comprehend this whole analysis, the derivation is very the understanding this in different terms of this equation is very important, and that understanding can only arise if you have yourself derived this equation. All right. So, this is once again the coupled equation that you get, d2t tilde dx square minus 1 by there is a 1 by Lewis number here, minus ddx tilde t tilde y tilde is equal to 0. Okay. Now, let us integrate this guy from minus infinity to any point inside x in. Okay. So, what we get is the following, that is we get d tilde dt tilde dx tilde in, okay, minus, or we will not call it in, we will just remove the in, and we assume that this t tilde that we get now is essentially anything is mentioned is within this within x egg and x and 0. So, this is only in the reaction zone. So now we are integrating within the reaction zone. Okay. Of course, this is equal to 0 because at x equal to minus infinity, this is 0 plus, again this is at x equal to minus infinity, this is 0 minus tu tilde plus 1, right. So this is the thing, this y tilde is equal to 1. Now at anything between, you see, if you remember the flame structure, so now this left hand side is between x sig minus x tilde and 0. So it is basically within this part. Okay. So what have we got in this part? You have got t tilde y tilde. Now we can assume that t tilde is essentially, compared to the other terms, this thing is essentially your tb tilde, or we can call it like t in tilde, which is essentially close to your tu tilde, your tb tilde, and this part is essentially your y in, and y in is essentially very small compared to the other terms. So is almost equal to 0 when compared to all these terms. Okay. And this is equal to tb tilde, and tb tilde is equal to tu tilde plus 1. So essentially you see this goes to 0, and this tb tilde is essentially will cancel with this thing. So all these things essentially cancel out. So what we are left with is dt tilde dx tilde plus 1 by Lewis number dy tilde dx tilde. But please remember, this holds only within the reaction zone. It is not entirely thing. It is not in the any part of the flame. It is only when you have left hand side in the reaction zone we can do this thing. So that is why the integration thing is important, where we are integrating it from. Okay, so dt tilde dx tilde plus 1 by Lewis number dy tilde dx tilde is equal to 0, and what you get by integrating is essentially, now if you integrate this equation from minus from x ig, well, so if you integrate this again, actually from say minus infinity to x ig x in, so that what we did before, we get t tilde plus 1 by Lewis number y tilde y in is equal to your t tilde is a tu tilde. Okay. Plus 1. Okay. So this tu tilde plus 1 is nothing but tb tilde. So we get essentially is y in is equal to tb tilde minus is essentially is equal to your Lewis number times tb tilde minus t tilde. Okay. So as you saw that, yeah, we considered here this to be almost equal to 0, but when we considered with respect to the other terms, but in general, yeah, this is small, because you see inside in this is essentially this tb in is tb tilde is almost equal to t in tilde. So indeed y in is very, very small. This is itself a small quantity. Okay, but itself it's, I mean, we can, by doing this we can estimate how small it is. That is the point here. Okay, and it is not 0, because if it was 0, then there would not have been a then there would be no right hand side in this temperature equation. So it is not 0 actually, but it is, what we have done here is that we have not considered it 0, we have just considered that this equation, this term is essentially smaller than these terms. So this term is essentially much smaller than this term and this term, which is a true assumption. So then we can write this y in tilde essentially is equal to your Lewis number times tb tilde minus t in tilde. So this is a very important thing, because now if you go back to this go back to our if we go back to our energy equation. Okay, so what we will get now, we can substitute this. We have got y tilde in is equal to Lewis number times tb tilde minus t tilde at the inner zone, t in tilde. Okay. So now we can substitute this thing inside our energy equation inside the inner zone. So integrating in the inner region, so everything is only within the inner region, so that must be kept in mind. So this was the equation. we have replaced the in because it's only within the inner zone, it's implied. So you see now this equation does not have any y. So now it is exact, is explicit in t tilde, and now we can do much more things with it, so we can integrate it. Now one more thing is that you see within the inner zone that now this is basically comes from diffusion, this we can understand, this comes from convection, and this comes from reaction. Okay. Now in the preheat zone we saw it's essentially a balance of your diffusion and convection, and essentially in the reaction zone what we can do now is that because the temperature gradient is so steep, we can consider only the higher order temperature gradients. Actually the first order temperature gradient is not so steep here, as you can see from this. Okay, so but the second order temperature gradient is large. So and this can be shown by integration also, that if you just do the integration you will see that this will give you the dt plus dx tilde minus dt ig dx tilde plus minus this will give you tv0 tilde minus t ig tilde, and then this will essentially is equal to minus dsc Lewis integral of these things, right, add over dx tilde. So this is very small because tb and tb0 is very small, which again suggests that this convection, the convection process inside a flame, inside the inner layer or the reaction zone is very small. Is small only in the inner layer. Okay, so that is why we can neglect these things, and we will only consider this convection is essentially will be neglected, and we will only in the inner layer we will only consider the balance between your diffusion and your and the reaction. So this part will go to 0. We will just neglect it with respect to this term and this term. This part is actually never 0 because of obvious reasons, but we will consider it to be small with respect to this and these things. So now if you consider that what we get is okay. So now this also integration is difficult, so let us do a small mathematical jugglery, that is this is it, right. So we can write this as right. This is exactly equal to this, and then we can put this inside this. Okay. So then we can substitute this whole thing here, and what we get is two comes from here. Okay, now we are ready for integration. So if we integrate, what we will find is that so this is the equation that we got. And then if we integrate this between x ig and 0 from here to here, if we integrate, from x ig from t ig tilde okay. Now if you remember this guy, this at not yeah, at x equal to 0, this is essentially equal to the right hand side, this plus. So this is essentially equal to, by matching conditions, your dt tilde dx tilde square at plus, which is equal to 0. Okay. So on the plus side, so essentially we can get rid of this thing, this goes to 0, but of course this does not go to 0. So this goes to 0, and we can write so from now on we will focus only on the RHS, because as we will see that because one we can also see that show that this by matching conditions, that is because this slope has to match this slope. So at x ig what is happening is that the temperature is increasing like this, right. So this is, if it is x ig, so the slope, because of the continuity, this and the smoothness, this slope has to match this slope. So essentially this on the this is the inner side and this is the minus side. So at this point this dt dx tilde x ig is equal to your dt tilde dx tilde minus at x ig, right, and this we obtain to be essentially is equal to 1. So this is becomes essentially equal to 1, and if you this came from this fact that if you remember that here dt tilde dx at x is equal to indeed, but this is integrated from the minus sign, tb0 minus tu0 is equal to 1. So essentially this is 1. Okay. So we will just focus on this right hand side from now, because the left hand side is equal to minus 1. So if you just remove the minus sign and put it here, then what we will get is essentially this 1 is equal to your minus 2 Lewis number times Damköhler number 0 times tb0 tilde to t ig tilde times tb0 tilde minus t tilde e to the power of minus ta tilde by t tilde dt tilde. Okay. Now let's consider, we'll just focus only on this right hand side now. Now let's introduce another change of variables where tau is equal to tb0 tilde minus t tilde. Okay. And you see we can also write it as like tb0 tilde minus tu tilde, because this guy is equal to 1. Okay. So that is a good thing about normalization, it becomes much simpler. So essentially then it becomes then this becomes is equal to we'll just consider this, if we just consider this integral, then this becomes tb0 then this is becomes 0, and this t ig becomes tb0 tilde minus t ig tilde times tau, okay, or tau dashed, or we will just represent this guy as tau ig, okay, or tb tau dashed minus e to the power of minus t. So if we substitute this now, t tilde is nothing but tb0 tilde minus tau. So we can write as exponential of minus ta tilde divided by tb0 tilde minus tau. Okay. So this is the thing, d tau dashed, tau dash. And then we can write, if we now bring the exponential downstairs, actually we should write it like in this form. Okay, and then this becomes, if you normalize both sides by TP0 tilde, TP0 tilde and TP0 tilde, what you get is 0 to tau egg, tau dashed, exponential of minus obviously 1 TP0 minus tau tilde, whereas this is a small quantity because tau tilde is close to TP0 tilde. So, tau tilde is definitely much smaller than TP0 tilde, and then if this is a small quantity we can write this as and this is, you see, if you recognize, this is the Arrhenius number. This obtained from the binomial expansion. Okay. Simplified into, this is what we can write. This is what we had, exponential of minus Arrhenius number times 1 plus tau and this can be essentially written as exponential of minus Arrhenius number times exponential of minus tau a tilde by TP0 tilde times tau by TP0 tilde. Now, this is 1 of course, and we can replace the 1 by TP0 minus TA. Okay. And then you see this becomes exponential of minus Arrhenius number times exponential of, this whole thing is nothing but Zeldovich number minus Zeldovich number times tau tilde. Okay. So, now if you substitute this full thing in this integral, what you get is the whole thing becomes 1 is equal to integral this 2 times Lewis number times Damköhler number integral 0 to tau egg is essentially equal to tau dashed times exponential of this also can actually go out. Now, this is only within the inner layer, okay, just remember that thing. Okay. So, this is the integral that we get. So, now if you integrate this further, what you get is and this integral becomes, there is a Zeldovich number square in the downstairs times 1 minus 1 plus Zeldovich number times tau e to the power of minus Zeldovich number tau. Okay, that is the integral. Now of course we can say that what you have is now you see that the Zeldo number appears on the in the numerator of the exponential. Of course it is multiplied with tau. So it is not obvious that it will go to 0, but if the Zeldo number is so large that it even can overcome this overcome this tau, then essentially this whole thing becomes essentially 0, and that is purely because of the fact that this is an exponential it is exponential in minus Zeldo number. So then this whole thing becomes 1. So we will consider that the problem is posed such a way that this whole thing goes to 0, or it's much smaller than much smaller than 1. So then this becomes 2 times Lewis number times ds is times exponential of minus Arrhenius number by Zeldo number. Now this closes the problem. Why? Because if you have to remember this definition of essentially the DAC, the collision, the Damköhler number, and that contains the collision Damköhler number, and that contains lambda by Cp times Bc by F0 square. Okay. Now let's substitute it here. So if you substitute this into this, you immediately see the F0 square comes in the denominator, so we can take it on the left hand side. So then it implies F0 square this is Zeldo number squared 2 times Lewis number times okay. Now this is this Bc times exponential of minus Arrhenius number is essentially your WB0, right? That is a reaction rate measured at the near the bound gas temperature. Okay, so so this equation then it becomes very similar to the scaling equation that we obtained previously, but of course you see that there is a Zeldo number square dependent, in contrast to the previous thing where we obtained that this like there was a Zeldo number to the power of 1 dependent. So of course when you do the, so here actually the 2 Zeldo number comes from, one comes from the reaction rate and the other comes from the fact that y, another Zeldo number essentially comes from the y in is essentially is proportional to 1 by Zeldo number. So of course when you did the scaling analysis you did not consider that, right? So that is where this comes from. So that is where this analysis, if you see, is much more revealing, and this gives a very nice expression of and shows you what this thing depends on, what the F0 depends on essentially. But this basic nature of the fact that F0 is essentially a geometric mean of your lambda by Cp and the reaction rate that is still maintained here, and so it is indeed that insight was indeed correct, but this is the complete expression. So as you know that the F0 is essentially rho u times SL u, that is SL0 or SLU, that is the flame speed on the burn side. So this essentially gives you the explicit expression for the flame speed, okay, and which you have derived. So I urge you to go through this derivation once more and be familiar with the detailed nuances of it. So essentially what you have done here, if you summarize, if we consider the Frank-Kamenetskii analysis, we have essentially separated the we have separately analyzed the preheat and the reaction zone, and we have neglected the reaction in the former zone, that is in the preheat zone, and the convection in the latter, and then we have matched the solution. So preheat zone analysis was this, that we considered the W to be equal to 0, and this we integrated once and we found this, and because T plus is, and in the equilibrium zone, of course your downstream equilibrium zone, that this is T dt dx tilde is equal to 0. Of course then we did the reaction zone analysis, where essentially we substituted the y in to be this Tb0 minus T in, and then we integrated in this form, and then we found that this is equal to this dt in dx squared is essentially at x at xig is essentially equal to 1, and then we matched it, and we found this this expression, this very nice expression of f0 square is equal to but this is what is in the slides essential for Lewis number 1, but we have not done it in the analysis. We have considered Lewis number to be not equal to 1, so it appears in the numerator if it is not so. So it appears this is a beautiful relation that you get, that f0 square, there is a burning flux squared is equal to essentially to 2 times lambda by Cp by Zeldo number squared times Bc times e to the power of minus T a tilde by Tb tilde. So you see that f0 is essentially proportional to 1 by Zeldo number squared. So one Zeldo number comes from the thin reaction zone of that analysis, and the other comes from the reduction in the reactant constitution in the reaction zone, and you see that this agrees well with this previous scaling analysis, but you see that you did not get the Zeldo number squared, we only get a Zeldo number 1, and also we did not get a factor of 2. It was correct except for the factor of 2 by Zeldo number. So extra Zeldo number we missed due to the concentration reduction in the reaction zone. Essentially in the reaction zone, the concentration goes from a small value yig or small y in, but it then goes to 0. So there is a reduction, it's not constant, so that where another Zeldo number comes from. So I'll stop here, and then in the next class we will go into how to measure basically the flame speeds, and how to basically find out on what parameters and basically understand on what parameters the flame speed depend on. The flame speed is a very important quantity. It's basically this quantity determines whether you can have a flame stabilized in a natural gas combustor, whether you have a flame stabilized in a premix combustor in an aero gas turbine engine, whether you can have a flame stabilized in a whenever there is a premix combustion happening, the flame needs to be stabilized. So this determines a lot in the flame speed. Of course you can stabilize flames which are much faster than the flame speeds, but that relies on something else which will come later. But the inherent property of the flame that governs flame stabilization is essentially flame speed. So you go over this in details, you do the analysis on your own hands and be comfortable with it, and this gives you a lot of confidence in premix combustion. So thank you very much, and see you in next class.